Okay, so it's just doing some troubleshooting, but I thought I'd make an interesting video. So the Z80, as well as the 8080, as well as the 8085, all have a multiplexed address. The upper 8 bytes, 8 bits of the address line come out straight, but the lower 8 bits are multiplexed between address and data. It's used for both things. So you have to latch the address. This is the latch that's used on this board. It's a 74573. That's a pretty typical modern latch. Back in the day they didn't have that part. They would have used a different part. But this one's nice because the layout is good. All of the input lines are on one side and all the output lines are on the other side. So somebody finally figured that out much later. Back in the days of the 8085, though, these parts weren't around. So let's take a look at that latch. It is like I say, an 8-bit latch, 8 inputs, 8 outputs, and then this latch pin. So that's the clock of the D-type flip-flops. These go into the Ds and those go out as Qs, and then this is the clock. So ALE is address latch enable, so pin 11. So let's take a look at pin 11, which is the address latch, and then we'll look at one of these data lines. We'll look at data line 0, AD0, pin 2, and output A0, pin 19. So that's what I have hooked up here. Let's take a look. So I'm using little micro clips. I'm on pin 11 down there with channel 3, and then channel 1 goes to the input, and channel 2 is on the output. So let's take a look at what we got here. We can see that the latch enable is toggling. It's giving little rising pulses here on the bottom trace. The top is the input and the middle is the output. Let me zoom in a bit. So you can see that whenever there's a rising edge of the latch enable, that's when this can change state. This top trace is the input. It can change state anytime it wants to. You can see here that the input has changed values, but this output has not, because there wasn't a latch enable here. But every time we have a latch enable, it captures the value of the top trace and stores that in the second trace. So we have a high, and then here we have a low, so when it latches it goes low. Here it goes high just long enough for us to latch, and here it's already low, it latches, so you can see that the latch enable is working. And that's all I was trying to figure out in this board was, is there data flow? Does the data look reasonable? Maybe the address latching wasn't correct or whatever. Anyway, I'm just going through it piece by piece, and this just gives you an idea of that latch enable. So once you have the address lines latched, now you have the upper byte and lower byte of the 16-bit address space to be able to be used. The data line is just used as is. There's no reason to demultiplex the data line. Whenever a read or a write happens, it's going to grab the value that's present on that bus. So here's an interesting feature I didn't know the Logic Dart had. I'm taking a look at the clock generation for the baud rate. The top trace is the input to the 16V8 GAL device. This is the 3.072 megahertz clock, and then it gets divided by 10 here to generate the 307 kilohertz, and then it gets divided by 2 once more to give you the 153.6 kilohertz. It's actually, yeah, 153.6 kilohertz. But if we look in here, it looks like there's some runt pulses. It looks like it's actually drawing in some little runt pulses. So this thing may have the ability to look at runt pulses, which is interesting. And that may trick the UART into thinking that there's a clock there that shouldn't be there. This one looks pretty clean. The 153 kilohertz looks clean, but the 300 does not, and I don't know why. So I think I'll verify that now on the oscilloscope to see if these runt pulses are real, and maybe this Logic Dart's a pretty cool instrument. Well, here we have that clock. I don't see any runt pulses. It is only a 4-volt signal. Let's look at our 5-volt rail. Yeah, 5 volts goes all the way to 5 volts. So these are going up to 4 volts. Here's the one that gets divided one more time. It looks about the same amount of dirtiness. Could be that there's just some ground noise that the Logic Dart was triggering on. It is interesting. This one does seem cleaner. This one does seem noisier. So it's possible that it is picking up that picking up this noise here. Let's take a look at it a little bit more. Yeah, there's some bounce there. Let's see if I can get a better ground. Yeah, better ground helps a little bit. I'm moving my scope probe. I have a long lead on the scope probe. I'm shortening that up. So I did have a long lead on the Logic Dart as well, so it probably just picked up some noise. So I'm not too worried about it. Alright, I did add a separate short ground lead on that probe, and it got rid of those runt pulses. So it was just a fixturing problem with the leads. But I did learn something new about the Logic Dart, that it will catch runt pulses. So that is really, really cool.